Welcome back, everybody, to INE's CCIE Data Center Nexus Switching Bootcamp. In our next section, we're going to continue our discussion with VPCs, and we're going to be looking at some changes in the first hop redundancy protocols in their behavior of using the 7Ks or potentially even the 5Ks as the default gateway of the hosts on the layer 2 LAN segments. So specifically, the first hop redundancy protocols that we're referring to would either be HSRP, VRRP, or GLBP, where HSRP and GLBP, those are Cisco proprietary implementations. VRRP is an open standard, but pretty much they're designed to do the same thing, where we're virtualizing what is the default gateway for the end hosts on the LAN. Okay, so from a design point of view, typically the Nexus 7K is going to be the boundary between layer 2 and layer 3. Where we're doing layer 2 switching down towards the end host. That's where we have our layer 2 trunking. Then upstream towards the core, we're doing our layer 3 routing in order to get us to our actual end users, like people coming off the internet, go into your data center, accessing your applications. Of course, you had to go over the layer 3 network in order to allow that. Okay, so this means that not only is the Nexus 7K going to be the VPC peers, so we have ideally different physical chassis that have the peer link together, that have the peer keep alive, then we have the VPC member ports. So they're virtualizing basically the ether channel between their devices, but they're also going to be virtualizing the layer 3 information with the first hop redundancy protocols. So in order to account for this, we're going to have to change some of the behavior of first hop redundancy, where normally we would have one active and one standby device. Or in the case of VRRP, I believe we call this the master and the backup. But in either case, the master or the active device is the one that is in charge of forwarding traffic for the virtual MAC address. So if we look at our physical diagram here, we have the two 7Ks that we're basically going to be using as our layer 3 gateways. So we're going to have some switch virtual interfaces that are on here. Let's say that we have VLAN 10 and we have VLAN 20. And then across the layer 2 link, okay, across our layer 2 peer link, we're including these particular VLANs in the allowed list because these VLANs are then going to be used on our VPC member ports. So down towards the 5Ks in this back-to-back VPC that we have, VLAN 10 and 20 are going to be forwarding downstream. Okay, then once we actually get down to the 5Ks, we have the 5Ks going down to the FHRPs, which is going to get us down to the actual end hosts. Now, the way that I have it set up in this case is I'm not doing the active-active on the FHRPs. So to simplify the topology a little bit, 5K1 is just going to 2K1, and 5K2 is going to 2K2. So we can get traffic flows that are coming up from this direction. See what happens when it gets to the VPC and then needs to go up to the switch virtual interfaces in order to route for our inter-VLAN routing down to the final destinations. So essentially the 7K here is going to be our gateway from a layer 3 point of view. Now the change that we're going to have to make is that when the traffic comes in on the VPC member ports, okay, we're still doing normal layer 2 Ethernet switching, which means that every time a frame comes in, we look at the destination MAC address. If we know it in the CAM table, we're going to send it out that port. If we don't know it in the CAM table, we're going to do layer 2 flooding. So the regular behavior of layer 2 Ethernet switching is not changing with VPC. The only thing that's changing is how we're doing the aggregation of the bandwidth of the physical links together. Okay, so the frame comes in, we look at the destination layer 2 MAC address. If the MAC address is going to the virtual MAC address of the first hop redundancy group, like the HSRP active MAC address or the VRRP active MAC address, it means that normally it is supposed to be going to the active device, the active layer 3 device of the redundancy group. So the potential problem we have then is that when we look at the actual traffic flow, if we were to have 7K1 as the active device, let's assume for both of our HSRP groups, and we have the second 7K as our standby for both of the HSRP groups, we would end up in a case that if traffic is received in the VPC member interfaces of the standby device, we would have to send this over the peer link to the active device in order to continue to forward it on upstream towards the rest of the layer 3 network. And again, this is going to be the behavior that we want to try to avoid in VPCs, that we do not want to use the peer link in the data plane. We ideally want to keep that just for the control plane synchronization, and then as a worst case scenario, we can kind of use it like a last-ditch effort data plane link. So then in order to fix this behavior, we need to change how the first hop redundancy forwarding is going to work. Okay, what is actually going to happen is that if the HSRP or VRRP standby device receives a packet that is going to the virtual MAC address, we are going to forward it as normal, as if we were the active member of the first hop redundancy group. So the end result of this is that the standby HSRP router is basically acting the same as the active HSRP router. So they are, in this case, active-active, not active standby, where under normal circumstances you would have to use GLBP, the Gateway Load Balancing Protocol, for this, where we have a decoupling of the active virtual gateway and the active virtual forwarder, where we have someone responding to the ARP requests on behalf of the actual forwarder, and then we're splitting the forwarding between different physical boxes. Where normally with HSRP and VRRP, we only have active standby forwarding, where one of the layer 3 gateways forwards, the other one is just listening as a backup for the primary to fail. But with VPC, that's not the goal that we're trying to accomplish. We want active-active forwarding on every single link, so we basically need to treat the HSRP standby as if it was the HSRP active device. Okay, now we'll also see that there's certain situations where we have non-standard protocols or non-standard applications that can break this behavior of the VPC. So there's certain features in some application switches and there's certain storage arrays that the way they have implemented their applications is when traffic comes into them and they reply, they do not reply to the HSRP virtual MAC address. They actually respond to the physical MAC address of the device that forwarded the traffic into them. So basically what this allows that application to do is to do symmetrical or synchronized forwarding based on the layer 3 device that forwards you the packet. So let's say, for example, we have two different routers. One is normally the active device, one of them is the standby device for HSRP. If the active router forwards you the frame, the source MAC address is going to be the burned-in address of the HSRP gateway. Okay, once that non-standard application replies, if they're replying to the physical MAC, not the virtual MAC, we're going to have some problems if the frame is then received back in on the VPC secondary peer. Because again, remember that the forwarding of the port channel or the ether channel is independent on each of the devices. So the 5Ks could be configured to do load balancing based on the source destination MAC address. 7Ks could be doing it based on the source destination layer 3 header and the layer 4 ports, because the goal is we're trying to get a more even distribution of the data flows over all the different physical links that we have. So in order to solve this problem then, because the issue that we're trying to avoid again is we don't want to use the peer link. So if the traffic comes in with the destination MAC address of the active forwarder for like HSRP or VRRP, normally the secondary VPC peer would have to send that traffic back over the peer link to get to them. And we don't really want to have to do this because again, we want to keep the peer link out of the data plane. So the solution for this is kind of a hack on the process that's called the peer gateway feature of VPC. And what the result of the peer gateway is that the VPC secondary, which is typically also going to be the HSRP or VRRP secondary, so the standby device, they are going to be proxying for not only the virtual MAC address of the primary device, but also proxying for the physical MAC address of the primary device. So in that particular case, if a frame comes in to the secondary VPC peer, the destination MAC address is the primary peer, but the IP destination is not the primary peer. So it's not something that is actually destined for them. It's not like a control plane or a management plane packet. It's an actual in-data plane packet. So if the IP destination is somewhere else, but the interim layer 2 destination is the active forwarder, the standby device, which is the VPC secondary, can continue to forward that normally without having to go over the VPC peer link. So in pretty much all cases where you are running first hop redundancy, and you're using VPCs, you would want to enable this feature on the 7Ks to make sure that you're minimizing the amount of traffic that is sent in the data plane over the actual peer link. So let's take a look back at our particular topology that we're going to be using here. So what we had set up in the previous example was that we have the back-to-back VPC that is going between the 5Ks and the 7Ks. So we have a VPC that goes up, and we have a VPC that goes down. Okay, then downstream towards the 2Ks, actually our topology is going to look a little bit different than what I have up here. So let me remove these additional crosslinks. And then we're going to use some of the end hosts for testing of this. Where on the first FEX, I have router 3, and I have server 1. On the second FEX, I have router 2, and I have server 3. Okay, so we're going to put these two together in the same VLAN. So let's say that router 3 and server 1, these are going to be in VLAN 10. And router 2 and server 3, we're going to put these in VLAN 20. So 2 different layer 3 segments, 2 different layer 2 segments. Okay, then on the 7Ks, we're going to have these 2 different layer 3 interfaces. So we have a VLAN 10 SVI, and we have a VLAN 20 SVI. This is going to be both on the primary VPC peer and on the secondary VPC peer. So not only are we doing active-active for layer 2 with the VPC, we're now doing active-active for layer 3 with the first hop redundancy protocols. Okay, so first let's go down to the end host configuration. So as we know, again, with the fabric extenders, those are controlled from the upstream parent switches. So the configuration changes here would be done on the 5K1 and the 5K2. They're not going to be done directly on the fabric extenders. So let's go to 5K1, and specifically the ports that I have here are going to be E11 and E14 of the FEXs. So it's going to be these 2 links here, E101/1/1 and E101/1/4. Okay, actually 4 to 5 would be the layer 2 channel there to the end server. So let's say here on E101/1/1, I need to shut this link down and change the speed to 1 gig. Okay, again, that's because the router's link in this case is a regular gig link. It's not a 10 gig routed port. So the speed is 1000, no shutdown. And then let me open up router 3's connection as well. So on router 3, let's show IP interface brief. And let's get rid of gig 01. I want gig 00 to be 10.0.0.3. Okay, so it's in VLAN 10. Show IP interface brief. Okay, the link is up. If we show CDP neighbors from router 3, we're not going to see the FEX as our layer 2 neighbor. We see the parent switch. But this does tell us what the FEX port is there. So it's E101/1/1. Okay, then let's go down to our end server. So in this case, this is this Windows server here that has the 2 10 gig ports. So it's got the converged network adapter, that's CNA. And let's look at the IP config. Okay, the team 0, so that's its logical port channel, is 10.0.0.10. So I need to change its properties here. Change adapter settings, go to the team properties, and then we'll say, so this is 10.0.0.10. The default gateway we'll say is 10.0.0.254. That's going to be our virtual address that we're going to use for HSRP. Okay, so if we say ipconfig, we have 10.0.0.10. Our gateway is 10.0.0.254, the virtual address. Okay, I should see that I have reachability to router 3 once I configure the access ports. So let's go back to the 5K, and we're going to put these both into VLAN 10. So let's show run interface E101.1.4 to 5. So these are the host ports that are going down to the server. So I'm going to put these in a channel. Let's say interface E101.1.4 to 5, channel group 10, mode active. Interface port channel 10 is switch port mode access, switch port access VLAN 10, and the spanning tree port type is edge. Okay, that would be normal because the FEX port is already going to be edge automatically. Okay, we also have VLAN 10 and we have VLAN, actually we just need VLAN 10. Okay, then on the link that goes to router 3, so it's E101.1.1, switch port access VLAN 10. Okay, we should see in the ping here behind the other window that we start to get reachability back to router 3 again then. Okay, so they're now both in VLAN 10. They have basic IP connectivity to each other. Okay, we need to do the same thing on the other side then. Okay, in this case, this is going to be the port that's going to router 2 is E102.1.1. So we'll say VLAN 20, interface E102.1.1, switch port access VLAN 20. Then I have interfaces E102.1.6 to 7 are going down to the end host. So this will be a channel group. We'll say channel group 30. Interface port channel 30 is switch port access VLAN 20. Okay, so pretty basic config on the 5Ks. We're just assigning the access VLANs to the downstream facing ports. Okay, then on router 2, let's look at its gig link here. We'll say that this is address 20.0.0.2 for VLAN 20. Then on the other server that's going to be on that same segment, likewise I need to set its address. So in this case, this particular server has the two 1 gig ports. So it has a 2 gig channel where the first server has the 20 gig channel. So our adapter settings, this is going to be on the team, which again is basically their logical port channel. Our address here is going to be 20.0.0.30. Default gateway is 20.0.0.254. That's going to be our virtual IP address. Okay, we then should be able to ping 20.0.0.2, which is router 2. Okay, so we now have basic layer 2 connectivity within the segments. Okay, you always want to test this basic stuff before you move on to any of the layer 3 routing. Want to make sure that there's nothing wrong with my VLANs, trunking, possibly VPC, anything else at layer 2. Just test connectivity within the layer 2 segments before you, well, like I said, go on to any of the layer 3 reachability. Okay, so our next step then is to go to the 7Ks, and we're going to configure the VLANs, both 10 and 20. We need to configure the SVIs. We need to do normal addressing. We would also need to do our routing. Okay, probably we have routing protocols like OSPF or FHRP that are going to send our traffic upstream to the core. Then last step is we're going to configure the HSRP info. So let's go over here to 7K1 to start. And I need to first create these VLANs. So I have VLAN 10 and 20. Same thing on the other side. VLAN 10 and 20. Now on the 5K, since I'm doing back-to-back VPC, I actually do want to create these VLANs everywhere because otherwise I can run into some inconsistencies there with the bridge assurance where some of the member links may be blocked and some of the member links may be forwarding for the VLAN because I want to make sure that the BPDUs are synchronized basically between the member ports. Okay, if I wasn't doing back-to-back VPC, I wouldn't necessarily have to do that because I would have separate links for the VLAN 10 forwarding versus the VLAN 20. Okay, so on the 7Ks, we need feature interface dash VLAN. I have interface VLAN 10. My address here is going to be 10.0071/24. No shut. Interface VLAN 20 is 20.0071/24. Okay, same thing on the other side. So let's say feature interface VLAN. Interface VLAN 10 IP address is 10.0072. Interface VLAN 20 is 20.0072. Okay, so now from either of the 7Ks, I should have basic layer 3 reachability to the end hosts. I should be able to ping 10.0.0.3 for router 3, 10.0.0.10 for server 1, 20.0.0.2 for router 2, and 20.0.0.30 for server 3. Yeah, again, you don't want to skip this step because you want to make sure that there's nothing wrong in the basic fundamentals before moving on to any other more complicated design. Okay, so the VLAN 10 is good there, and then 20.0.0.2 and 20.0.0.30. Okay, so now basic layer 3 reachability up to their layer 3 interfaces is working. Now, if I were to go to the end hosts, and let's say I wanted to ping between server 1 and server 3, of course, at this point, that's not going to work because I have their default gateway configured as the .254 address, and we have not yet configured any of the first hop redundancy. So either I would need to change their addresses to actually be the .254, like on the 7Ks, or in this case, we're going to be using HSRP in order to do that. Okay, this configuration is going to be pretty straightforward. There's nothing really fundamentally different between HSRP on the 7Ks or the 5Ks versus on regular Catalyst iOS. So if we take a look, let's start from the main documentation page, just so everyone knows where this is located. So from the main doc page, if we go down to switches, to data center switches, Nexus 7K, config guides. This is going to be part of, I want to say this is going to be under unicast routing, then under first hop redundancy. Okay, so we have GLBP, HSRP, and VRRP. In this case, we're going to be using HSRP. So it supports both IPv4 and IPv6. Functionality is similar between the two of them. Okay, really the only thing I want to see is just what's their config example. Okay, what does the syntax look like? I already know what HSRP does. I just want to know how do I actually implement it in Nexus. Okay, so we can do authentication. We can see here this is a keychain authentication, which means that we can do automatic time-based rollover of the keys, where I could say, we're saying in this case, from June 1st, 2008 to September 12th, 2008, we're going to use this first password. Once August 12th comes around, we're going to start to roll over to the second key. Then we're eventually going to stop sending the first key and start sending the second key. Okay, so notice there's some overlap between the two of them here. This is just like you would in regular iOS or Catalyst iOS. When you're doing keychain-based authentication, you want to make sure there's some overlap so that one key doesn't stop being active before the second key starts. Then you would have a problem with the control plane adjacency and ultimately start dropping packets in the data plane. Okay, then we have the actual HSRP config. Turn the feature on. We could do enhanced object tracking. In this case, they're saying look at the IP status of Ethernet 2/2. If this goes down, then we are going to decrement our HSRP priority by 20. So as long as the other remote peer has a priority that is between 70 and 90, let's say their priority is 80, if we were to lose this link, it means that they would then take over the active status. So it's the same logic as regular iOS, same logic as Catalyst iOS, just the difference is that we have this HSRP mode at the link level. Okay, so let's go ahead and add this. On the 7Ks, we need to say globally feature HSRP on both of them. Then on interface VLAN 10, we're going to have HSRP. Okay, we could give it a group number, or you could use just group number 0. Really, the only thing that I need to set here is just what's the IP address. Okay, the IP is 10.0.0.254. And I'm going to say that my priority is, let's say that I'm going to be the highest priority because I'm the primary VPC peer. Yeah, we'll actually see that this is not really going to matter what the priority is because the end result is not going to be active standby forwarding with HSRP. It's actually going to be active-active. But I'm going to do this just for clarity so we know which one is the active forwarder. Okay, the same thing we're going to do for VLAN 20. So HSRP 1, IP is 20.0.0.254. Priority is 255. Okay, same thing on the other side. So interface VLAN 10, HSRP 1, the virtual IP is 10.0.0.254. My priority is 100, so it's lower than the other side. HSRP 1 IP is 20.0.0.254. Priority likewise is 100. Okay, I then want to make sure that they're adjacent with the HSRP control plane. So let's say show HSRP. It says for VLAN 10 and VLAN 20, there's two different groups. Okay, VLAN 10, I am the standby device. The virtual address is 10.0.0.254. The active router is 10.0.0.71. This tells me that the adjacency has been formed. Okay, so the active router knows about the standby router and vice versa. Okay, the second group, the local state is speak. This means that they're currently in the process of converging. So if we check this again, ideally we should see that we are standby. Okay, the priority is 100. Their priority is 254. So they are the active forwarder. Okay, so pretty straightforward. Of course, you could change these other options like the authentication. You could change the virtual MAC address if you wanted to. You could do enhanced object tracking. You could change the timers. But that stuff is going to be the same in HSRP on other platforms as it is on Nexus. It's just different syntax to interface with it. Okay, so let's look at now the end host. Now routing should be working. Okay, we're still pretty much on the same segment, so the latency is going to be really low. It's going to be less than 1 millisecond, as we would expect here. Okay, let's look at the actual data transfer then. So here on the server with the 10 gig NICs, let's go to our JPerf that we're using yesterday. This is our TCP traffic generator. I'm going to say I'm the server. Okay, I want to look at the throughput in gigabits per second and then run the process. Second server, I'm going to do the same thing. So let's go to JPerf. The server's address is 10.0.0.10. 10.0.0.10. I'll make the counter really high, so it just continue to send packets. Let's look at this in gigabits per second. And then I want a large TCP window and maximum segment size. Let's say 8960, again, for the MSS. So that's 8960 plus 20 bytes for the TCP header plus 20 bytes for the IP header is going to get us to 9000, which would be our jumbo MTU. Okay, now I didn't actually enable jumbo MTU on the 5K and the 7K yet, so it's not going to be as efficient as it could potentially be. Okay, we see now we're getting about 88% of the link, maybe 90% of the link or so. Okay, again, as we saw yesterday, we're not getting 2 gigs, this is a 2 gig port channel, and the reason why is I'm only generating 1 flow right now. If I want to get higher than this, I need to generate more flows because the single flow still cannot exceed the bandwidth of one of the physical members of the port channel. Okay, so port channeling really only makes sense if you have more than 1 data flow, which in reality you will. Okay, so let's say 16 flows. Our aggregate should get somewhere around should get somewhere around 2 gig, which it's not here. Okay, it's still around 90%. Okay, what does this mean now? Why would I not be getting really the aggregate bandwidth of the link? Actually, there it goes. Okay, so it just took a while for TCP to go through its slow start. If I did not get this value up to about 2 gigs, it means that my load balancing mechanism is wrong. Because the IP address pairs and the MAC address pairs between these two servers is the same. What I would need to be looking at is the layer 4 port information to give some more degree of randomness to the flows. Okay, so let's now look at the physical links and try to figure out where are these flows actually physically forwarding. Because from our point of view, we really don't know what's going on with the traffic flow because there's so many possible links that we could be using. Okay, I know at a minimum that the traffic is coming from server 3. Okay, server 3 is the initiator. It's sending this basically just random TCP data. It's getting to the FEX. Okay, the FEX should be sending it up to 5K2. So if we go to 5K2, and if we were to look at show interface port channel 30, we should see that the input rate is going to include that bandwidth. Okay, right now this is the 5-minute average. So if we waited about 10, 15 minutes, it's going to start to climb up. But for the sake of brevity, let's go to the port channel and say the load interval counter number 2 is 30 seconds. Okay, so you can actually have multiple counters. You can look at like a 30-second average and a 5-minute average and an hour average if you want to. But I just want to know what is the megabit per second rate. Okay, so it's about 2 gig. From the 5K, I then need to know where is this going upstream. Okay, is it going out these links or is it going out these links? So let's now say show interfaces E1 8 to 11 and include megabits per second, or let's say include output rate. So it happened that the 4th member of the channel, which is E1/11, is getting pretty much the aggregate of the bandwidth there. Okay, so again, this is going to be pseudo-random based on the whatever the port channel load balancing mechanism is. Okay, so now the traffic is forwarding up to 7K1. This is what we would expect because this guy owns the virtual MAC addresses of the first hop redundancy. But let's now say that those links are disabled. So for whatever reason, there's a failure, and I don't have access to go via these links. Okay, the only way I have left is to go via 7K1-2. Now, this should not change my HSRP roles because it really doesn't have anything to do with the upstream 7Ks. This is some failure downstream. So I'm going to go to interfaces E1 10 to 11 and shut these down. This should not impact my end application. Okay, you see a small dip there while it's converging. But we're back to about line rate. If we now look at the distribution of the traffic, it should be using those first 2 links, or at least one of them. And this is going to start to climb for the first couple links. Let's look at the show port channel summary. Okay, links 8 and 9 are up, links 10 and 11 are down. So we can only forward over those 2 ports. So let's show interface E1 8 and include the output rate. Let's actually say input or output. Input or output. and then E19. So here's our output rate. Okay, so it turns out to be that the second link of the channel, E19, was chosen for these flows. And the reason why only one of the links is being chosen, if we show port channel load balance, the default mechanism right now is source destination IP and source destination MAC. There's no change between those two fields for these flows. Okay, there is a difference in the layer 4 port for TCP that we're using, because the TCP sessions are different for each of the flows, but the layer 2 header and layer 3 header is the same. So it's classifying these all as the same flow, lands on the same member of the channel. If I did not want that to happen, I could say include the layer 4 port information, then we would see a more equal distribution of the traffic. Okay, but for this example, it doesn't really matter which physical links that it's using. Okay, the only thing that I really care about now is that it is using that link that's going up towards 7K2. So the traffic came in down here. Now it's forwarding up here. Now this device, again, this is not the active HSRP address. So normally what would happen is that I'm going to have to send the packets this direction to get to the .254 address, because this is the virtual gateway. And we would see this if we go to 7K2 here and look at the show ARP, show IP ARP. Let's ping 10.0.0.254 and ping 20.0.0.254. And let's look at the show IP ARP. Okay, we can see that these addresses, these are the HSRP virtual MACs. This ACO1, or the 0C07 ACO1, this is the format, the standard format for HSRP. We then see there's the actual physical MACs for the remote ends. Like if I were to ping 10.0.0.71 or ping 20.0.0.71, and show IP ARP. Okay, we see, of course, there's a difference between the physical burned-in MAC of the VLAN interface on the other side and then the HSRP forwarder. But now we want to know, once the traffic has gotten up to this VPC peer, which again, this guy is the secondary. If we show VPC, we are the secondary. Okay, port channel 5, this is our downstream facing link. If we look at the show standby, or not show standby, show HSRP on this platform, we are the standby. Okay, so we should not be forwarding packets for these layer 3 destinations. We should be normally forwarding them to the other device that is the active HSRP forwarder, which means that they would be going out the peer link. So now let's look at, of these physical ports that we have, where is the traffic actually going? Let's say show interface E2 9 to 14. Okay, so it's basically all of those F1 ports on the right there. And let's include the, let's just look at the, let me see, what do I need to parse here? Let's say include Ethernet 2/ or megabits per second. Let's see, Ethernet 2, include, I missed. And actually, this needs to be bits per second. So the output rate is sampled differently than the input rate. There we go. Okay, let's say that pipe, and let's see, can we do another pipe? No more. There we go. Okay, so the physical traffic then is going out on E2/13. Okay, E213 is the VPC member port. It's not the VPC peer link. Okay, if this was not a modification of the behavior of HSRP, what we would see is that the peer link would be in the data plane for these particular flows, and then again, that's not going to be the ideal behavior. Because the peer link, we want to keep that just for the control plane. We can use it for some some really necessary data plane traffic. We'll see multicast is going to be one of the cases shortly. Then in the case that we have orphan ports because of a failure, we can use the peer link as a last resort. But the change of this HSRP, VRRP, and GLBP behavior is going to make sure to try to keep that traffic off of the peer link as much as possible. Okay, so really there's nothing that you need to configure in order for this to happen. As long as you're running the first hop redundancy protocols with VPC, this will be the default behavior. Okay, the other difference is going to be what happens when traffic goes to the physical MAC address of the HSRP devices. So from router 2, if I were to telnet to 10.0.0.254, let's see, can we ping 10.0.0.254? Router 2 is not routing yet. Let's say IP route. Actually, let's turn routing off. No IP routing. IP default gateway is 10.0.0.254, or actually 20. Okay, that's our VLAN. Ping 20.0.0.254. Okay, so that's our gateway. If we telnet to 10.0.0.254, and let's log in here, we end up on the first 7K. Okay, so in this particular case, this is the active device, so it's the active HSRP forwarder. The traffic was actually forwarded towards them because the layer 2 destination was the virtual address, but the layer 3 destination was the virtual address as well. Okay, for the end data flow, so something that's not actually going to the switch itself, the destination layer 3 address is not going to be the local SVI. So this is the reason in the case of the servers with the JPerf, the actual TCP flows do not go to 7K1, but something that would be like in the management plane, like our telnet here, that traffic is actually going to the active device because it's destined both for the layer 2 and for the layer 3 address. So really to demonstrate the other problem, let's see if we can do this by doing a static ARP in the end servers. So let's go to 7K2 and look at the show IP ARP again. Okay, this is the physical address of the of 7K1. Okay, so that's the SVI interface. And what I'm going to do now is let's stop the transfer. And let's go to the Windows CLI and let's say ARP-A. I want to see what is the MAC address for my default gateway, 10.0.0.254. Okay, we can see that this is the virtual HSRP address. And let's see, can we do a static ARP? Let's say ARP-S 10.0.0.254, and then I'm going to put the physical MAC address. So let's say ARP-A. And I may need to delete the other ARPs first. Let's say ARP-D star. So a static ARP, then ARP-A. Up top. Okay, so here's the static entry is listed in there. Okay, now let's see what happens when, and let's actually do this on the other server as well for completion. So let's say ARP-A and ARP-D, that's going to delete it. So ARP-S was static. What my gateway is 20.0.0.254, and I'm going to set this to be the physical address of the first 7K. And ARP-A. Okay, so the static entry is in there. So basically what's going to happen now is the layer 2 frames that the 7Ks are going to be receiving are going to have the destination MAC address of the physical MAC address or burned-in address of the SVI on the active forwarder. So this represents that kind of non-standard application that would be modifying the layer 2 behavior of frames to try to reply back to the person who sent you the request. Okay, so let's go to the end application, and let's start the listening of the server again. Let's go to the client, connect to the server. Okay, we can see our flows are working. Okay, what we should now see that is going to change is that if we go to 7K2, let's look at that same show command again. Show interface. These are the range of the layer 2 links that I have, and I want to know which link is using the large amount of bandwidth. Now it is E2/13. Okay, E2/13 is still that same member link here. So let's clear the counters on the interfaces. Let's show VPC as well. It says the peer gateway is disabled. Let's look at the show HSRP. Local is standby for both groups. And I may not get it to be able, I may not get it to have this behavior using the Windows machines. Let's see, did it actually? Here, what we could do, let's try this from the routers. Let's go to router 2, actually router 3 first. I need to do the gateway config here. So no IP routing. IP default gateway is my HSRP neighbor 10.0.0.254. Then let's ping the broadcast address. Okay, this should give me responses back. If we show ARP, actually Nexus doesn't respond to broadcast pings. Let's ping the .71, the .72, and the .254. Okay, so I want to know what is the physical address of the 7Ks, and actually I need to be doing this from router 2 because router 2 is on the right. So let's ping 2020 or 20.0.0.71, 72, and 254. Then show ARP. Okay, I'm now going to do a static ARP. ARP for 20.0.0.254 is the physical address. And this is ARPA. Let's clear the ARP cache, show ARP. Okay, so now we have the physical address installed as the virtual MAC. If I now do a ping to router 3, let's say ping 10.0.0.3 with a high repeat count and a timeout of 0, we're going to be generating tons of packets here. Okay, if we look at now the counters of the link, and this one's going to be a little bit tougher to see. Let's say let's show the interfaces again, and let's include the output packets. And what I'm going to do, let me stop that transfer on the end hosts. So that's generating lots of packets. Then let's clear the counters. So this means now Ethernet 2 or output packets. E210 is where these are all going. Okay, these are all the pings that router 2 is generating. Okay, E210, if we look at the physical diagram, is the VPC member link, or excuse me, the VPC peer link. Okay, and that's again not what we want in this case. So if we look back at the data flow, and again, normally this is not going to happen. It's only going to happen when there's a non-standard application that is changing the MAC address of who they are replying to. But in the data center, there are a bunch of things that do that. There's some applications by like NetApp and EMC that try to optimize the replies for like storage by changing the behavior of what is basically outside of the standard of Ethernet and outside of the standard of normal IP behavior. So we basically need an additional hack to solve this problem with VPC. Okay, so the packets are coming from router 2. Okay, they go from 2 to the 5K. The destination MAC address is the burned-in address of this VLAN 20. Normally, the destination MAC address would be the virtual MAC of HSRP. So if it was the virtual MAC, it would go up this way and then down the VPC member port. Because again, we're trying to avoid using the peer link, we're trying to keep the traffic as local as possible. Okay, but in this case, what is now happening is the packets are going up to 7K2, they're going across the peer link, then they're going to go down the member to the destination. So let's now go to router 2. Let me stop this ping. Let's go to our VPC members. Okay, VPC domain 7, I want to say this was. Let's say show run VPC. VPC domain 7, and we want the peer gateway feature on. It says IP redirects have been disabled. Peer gateway is enabled. Disabling IP redirects on all interface VLANs of this VPC domain for correct operation of this feature. Okay, because now we're basically doing proxy routing on behalf of the other VPC peer. And I need to say this on both ends. So let's say VPC domain 7, peer gateway. Now, if we show HSRP, what is not going to change is that, let's say, show HSRP, include group or state. Okay, for both of these groups, I am still the standby router on the secondary VPC peer. But now let's clear our interface counters, and we're going to look at that interface output again. Okay, those first two links, E29 and E210, those are the peer links. E211 to 14, those are the member links of the VPC. So let's go ahead and send the ping again on router 2. I want to know where are these packets going. They're now going out the VPC member ports. So this is the change in the behavior then of that peer gateway feature. What it's saying is that even though I am not the active HSRP forwarder, when a packet comes in that is going to the MAC address of the other device, okay, so the other VPC peer, the layer 3 destination is not them. Okay, if the layer 3 destination was 10.0.0.254 or 10.0.0.71, that's got to forward over the peer link. Okay, because that would be like management traffic, like a telnet or SSH or maybe SNMP polling, something like that. We want to make sure that actually lands on the correct device. But in this case, the layer 3 destination is just transit from the Nexus's perspective. It's not going to me, it's going to some end host. Okay, so the packet comes from router 2, it gets up to 7K2. The destination MAC is this guy. But I'm not forwarding it towards them. I'm going to do proxy routing on their behalf and then send it down the VPC member link. And the key here is that this is not the default behavior. You do have to enable the feature. You probably would want to do this by default when you're turning on first-hop redundancy along with VPC, because if you do have some sort of non-standard application, we want to make sure, again, to keep the traffic off the peer link as much as possible. But again, beyond that, when we look at the configuration, there's really nothing special about the HSRP config. Just at the interface level, we have the IP address, we could do authentication, we could change the timers, we could do enhanced object tracking. Really the only change is that when we look at show run VPC, we're saying that for the first hop redundancy protocols, we're changing the way that we look at the layer 2 MAC address destination in the header and then determine should we be the one who's locally forwarding that, or should it go over the peer link to the remote VPC peer? Okay, so we have a couple questions here. Would you still do an HSRP domain per VLAN? Yes, you would, because each VLAN is going to have separate layer 3 addressing. So you need a separate HSRP group. Okay, it doesn't have to be a different number. Probably for clarity, you would want to match the number of your first hop redundancy group to the VLAN number. So it would have made more sense if I said this was HSRP 10 and HSRP 20. Just from a verification and troubleshooting point of view later, I know that group number 20 means VLAN 20. I don't have to look at the rest of the config. But technically, the number is just arbitrary there. There's a question, in what kind of scenario would FHRP tracking make sense if both members are active forwarders? Okay, the case that you would not want to be a forwarder is when you have layer 3 uplinks to the core that fail. And there is a design document on Cisco's website that talks about this, but basically the potential problem could be that we have, so layer 2 is down here. Okay, layer 2 is down here. The 7K is the demarc between the layer 2 and the layer 3 domain. So this is the regular IPv4 network. Maybe it's the IPv6 network too, okay, up here in the core. So we have layer 3 uplinks. If the destination is actually out that direction, I would not want the HSRP secondary, or actually the standby device, to forward on behalf of the active router if this link is down. Because then in that case, the traffic would be going over the peer link and then out. If this link is down, what I would actually prefer the forwarding to look like is this, just to avoid them completely. Now, we would have to test that. I'm not 100% sure. If you decrement your priority to 0, the router is supposed to remove itself from the standby process, but I haven't actually tested that on NXOS. I'm not sure if that's the same behavior as the rest of the platforms. So if you want the forwarder to just completely stop, you say you create a tracked object, and you say if this object goes down, then decrement 100% of my priority down to 0, which means I don't participate in the election at all, and then I would not forward traffic. Okay, but the worst case scenario that's going to happen here is that you use the peer link. You're not going to drop traffic, it's just that you don't want it to go over the peer link if you have the option to not do that. There's a question, why would we use HSRP with VPCs? VPC itself provides load balancing. Can you describe a scenario why you would use this? For the end users actually trying to route to the applications that are in the actual DC. So let's say here, like these end servers. So if server 1 down here is a web server, so this is our web server. Yeah, ideally we would have more than one, but let's say this is our web server. The traffic is going to have to route there over layer 3 somehow. So it comes over the regular public internet, gets into the data center. It means that it has to go through layer 3 routing in order to get there. If you're only using the data center applications for link local communication, if you're not routing publicly to the rest of the network, then you wouldn't necessarily need to use a layer 3 gateway at all. There are some applications that you do not need to use routing for. Some of them would be like if we're doing virtual machine mobility between data centers, like with something like vMotion, you would not need a layer 3 gateway on the VMware host machines technically to do that. You probably would want to so you can route to the machine like for management, but technically that communication would be link local just over layer 2. So really you're normally going to have a default gateway for everyone. Okay, there's another question. What's the reason of keeping the control plane separate in VPC as opposed to VSS? So again, remember with the virtual switching system for VSS for 6500, there's a single control plane, where VPC we have 2 separate control planes. It actually has to do with the next topic we're going to go into after this, which is related to the failure scenarios. In the case of VSS, if there's a failure of the VSL, the virtual switch link that is basically like the peer link, that is considered a catastrophic failure for VSS. that you end up in a dual active scenario where both of them are forwarding, but since there's only one control plane, they're sharing the same IP addressing. So let's say you have your 6500 that has VLAN interfaces and you're doing layer 3 routing to it, like you're running OSPF to it. This means from the other OSPF neighbor's point of view, that's the same IP address between the two chassis. In the case of VPC, it would be two different IP addresses because it's two different control planes. So if there's a split in the middle and the VSL goes down, you have your 6500 chassis 1, 6500 chassis 2, both with the same addresses that are now trying to form OSPF adjacency. That's going to cause a corruption of the database, and now you lose all layer 3 reachability. So with VSS, the failure of the VSL is always catastrophic. In the case of VPC, there are cases where we can recover from that and then fall back to like spanning tree as our kind of last-ditch effort forwarding. There's a question, why would there be any downside to enabling the pure gateway option? I'm not really sure what the negative would be. There may be some strange applications you have that it doesn't work with, but I probably would put it on there. There's a question, if router 2's outgoing packets only hit 7K1, would the ARP entry learned in 7K2 eventually time out and cause the incoming packet going through 7K2 to be broadcast? Yes, it would. Okay, because at the end of the day, we're still doing normal layer 2 forwarding with Ethernet. So that means that if the CAM table times out, and not necessarily the ARP cache because we're doing layer 2 switching, not layer 3 routing in this case, but if the CAM table times out and we don't know the MAC address of the destination anymore, then we're going to have to flood the frame. Okay, flooding of the frame will go over the peer link, so your normal MAC address flooding, it will go over the peer link, but based on that VPC check rule, you will prevent the looping of the frames. So the packet comes in the peer link, you're not going to send it out any of the local member ports, assuming that the remote VPC peer has active VPCs available, which is that kind of complicated rule we talked about yesterday. There's a question, can a 7K be a VPC peer with a 5K? I don't believe so because of the hardware check and the consistency check. I'm not 100% sure though, I haven't actually tried that. I'll try that out and let you know whether you can do that. I would assume, off the top of my head, probably not, but you'd have to test it out to see. Someone has a comment, the F5 load balancers use auto last hop and NetApp uses fastpath source MAC address caching. That's exactly what the problem is, the applications like that. Both of these features can be disabled on these appliances. Yeah, so you could turn it off. Probably that might even be an easier solution because then you don't have this additional proxy routing, but it is a possible way to fix it. Is this also the default behavior for IPv6 with VPCs and first hop redundancy? It is. So you try to keep that rule of locality where basically you don't go over the peer link. There's a question, is the peer gateway reliant on back-to-back VPC to work? No, it is not. So it's just secondary that the design we're using is VPC. In this case, it doesn't have anything to do with the 5Ks. This is only a behavior on the 7Ks that is changing. Another thing, also for after class, feel free to ask these questions on our online forum as well on IEOC. There is a data center section there. So if there's anything that we don't get to right now, feel free to ask the questions there and we can field questions there as well. There's a question, how does NXOS handle a scenario when it learns the same MAC address of a server seen on two different links in the same VLAN via a VPC member link and the VPC peer link? That actually would be the default behavior. So it is going to learn the MAC address on the peer link and it's going to learn it on the member link, but there's just a fundamental behavioral change that you don't use the one that's on the peer link. Okay, the only case that you put the MAC address in the CAM table pointing out the peer link is that if your local VPC is down and basically you have to use the peer link because there's an orphan port on the other side. So it has to do with failure scenarios. You can do that but normally you don't. You normally don't learn MAC addresses on the peer link if you can prefer to learn them on the members. Okay, there's a question, can I describe the different functions of primary over secondary? We're going to talk about that next as we go through some of the failure scenarios. Okay, so really the key for this example is that first-step redundancy basically just works on its own with VPC. There's nothing special that you have to do. So it will try to forward the traffic not over the peer link. Really the only issue comes in when you have those non-standard applications that are changing the layer to header differently than what it normally would be under just regular forwarding, and then you can use that peer gateway feature in order to fix that problem.